Today we're going to learn how to calculate the formula for the distance of a point P given by coordinates x0, y0 to a line given in the slope-intercept form, which is y is equal to mx plus c. In other words, we are interested in finding this distance d. So let's get started. The first step in our proof is to draw some intercepts from the point P to the line. The horizontal intercept, which is parallel to the x-axis, and the vertical intercept, which is parallel to the y-axis. This will make our life easier. As we'll see later, these lengths are easier to calculate than d directly. I'm also going to label these points for clarity, the point A and point B, and also the corresponding lengths. I'm going to label lowercase a and lowercase b. The idea of the proof is to rewrite d in terms of a and b, as a and b are much easier to calculate than d directly. One thing to note is that the triangle APB is a right angle triangle because AP is parallel to the y-axis and BP is parallel to the x-axis. So I'm going to label the length of the third side AB as h, which is the hypotenuse of the triangle APB. Now let's see how AB, D and H are related. In order to do that, let's write the area of the triangle APB in two different ways. So area of triangle APB is half times base times height. Let's say the base is the hypotenuse edge, which is h, so the height in that case will be d. If the base is h, the height will be d, and area is half times h times d. But we can also choose a different base for the triangle. Let's say BP is the base. In that case, the height is AP. So the length of the base will be B and the height will be A. And the area is also half times B times A. Rearranging a little bit, we can see that H times D is B times A, or D is equal to A times B divided by H. So as you can see, if we know A, B and H, we can find D. And the idea of this proof is that it's simpler to find A, B and H than D directly. So let's see how we can further replace B and H in this equation. As we know from Pythagoras' theorem for a right angle triangle APB, the hypotenuse squared is equal to a square plus b square. H square is a square plus b square. So h will be square root of a square plus b square. So we can substitute h in our formula for d. D becomes a times b divided by square root of a square plus b square. Now if we look at the slope of the green line here, we know from the equation of the line that the slope is m. But as we know, the slope is defined as rise over run, or in other words, delta y by delta x. So from the triangle APB, we can see that the rise is a and the run is b. So we can write m as a divided by b. Rearranging this, we see that b is a divided by m, and we are only interested in magnitudes here, so I'm going to put an absolute value symbol around this because m can of course be negative. In this case we are calculating distances or lengths, which are always positive, so assume absolute values for lengths in these equations. So now that we know how to substitute b for a, let's put this back into the formula for d. So d becomes a times a divided by m divided by square root of a square plus a square by m square. In other words, a square by m, the numerator, multiplied by square root of m square divided by a square m square plus a square, which can be written as a square by m times m by a. Here we brought out the square terms, times square root of m square plus 1. And simplifying further, d will be written as a divided by square root of 1 plus m square. So now we have written d in terms of just a and m, and the final step will be to find the value of a. We already know the coordinates of p, x0, y0. So let's see if we can write the coordinates of a. The x coordinate of a will be the same as x0 because a and p lie on the same vertical line. This is x0 on the number line. It's a shared coordinate. And the y coordinate of a can be calculated by noting that a lies on the green line. So its y coordinate is given by the equation y is equal to mx plus c. So substituting x0 there, the y coordinate of a will be mx0 plus c. Now distance a can be calculated by doing the difference between the y coordinates of p and a. So this will be mx0 plus c minus y0. So the y coordinate of a minus the y coordinate of p. And I'm going to put an absolute value around it because it's a distance. So this is the formula for a. Now if we substitute this formula for a back into the equation for d, d will be mx0 plus c minus y0 divided by square root of 1 plus m square with an absolute value around it. So the general case formula that we found says that d will be absolute value of mx0 plus c minus y0 divided by square root of 1 plus m square. However, as you can see, this relies on there being a valid slope m and an intercept c. This does not always apply, as we can see in the special case here. In the special case, the green line is completely vertical, so the equation of the green line will be given by the formula x equal to k. So in that case, as this line becomes more and more vertical, m will tend to infinity, and when it's completely vertical, m is not defined, and also there's no y-intercept c as well, so we need to modify the formula for this case. The formula for this case is quite trivial. If there's a point P with coordinates x0 and y0, the distance from point P to the line will simply be the x offset between the point P and the line. This distance will be simply the difference between x0 and k. So let's write that formula. So for the special case, d will be given by the difference between x0 and k with an absolute value around it. So this is a special case formula for when the line in question is completely vertical.